All right. So again, my name is Chris Meert. I'm about to finish my fourth year PhD at the University of Michigan. Today I'm going to talk about some detection concepts for active interrogation. So it's pretty easy to start out with some background and motivation. Yesterday we talked mostly with a boss about some physics for active interrogation and some important details I think we should remember as we talk about active interrogation is to just call back to the passive sort of scanning for cargo. Again, remember that the time correlated neutron emissions are characteristic of special nuclear material, and so that's a very valuable signature for us to look for in these situations. But of course, that passive emission rate will vary based on the material. Something like plutonium-240, which undergoes spontaneous fission, that can emit neutrons on the order of 1,000 neutrons per seconds per gram. However, if you're looking for other material, something like uranium-235, you can be as small as 3 × 10⁻⁴ neutrons per seconds per gram. So you can imagine if you're trying to inspect cargo for this sort of material, we may encounter some challenges here. For example, in the port of Los Angeles, which I've shown an incoming container ship on the right here, they receive about 26,000 cargo containers per day. So if you say, maybe we should inspect all of these, and what if we spend only a minute on each of these cargo, we're looking at 433 inspection hours per day, which is daunting to say the least, let alone the fact that trade will be time sensitive. So this is sort of the challenge we're up against in these situations. So perhaps these passive methods may not cut it here. And so, of course, for this presentation, what's something we can do to shorten these inspection times, make it easier? That's active interrogation. Some advantages of this method would be to create much stronger radiation signatures compared to the passive signatures. Of course, Abbas compared and contrasted those yesterday. We can also, since we're using interrogation sources, penetrate radiation shielding. And sure enough, on the right here, I've included a sort of CAD model of one concept called the nuclear car wash. You can see you can set up neutron generator, you can set up detector arrays, and you can even scan cargo as it goes through. Of course, like anything, there are advantages, there are challenges. In this case, we're looking at dose to personnel as being an issue. Activation of cargo, that's especially concerning if you were to use, say, a neutron source. This will also create a very challenging detection environment because we are using very strong sources of radiation. And lastly, we will have a cost to consider. That's very common in nuclear engineering applications or engineering applications in general. So the sort of overview of all of these methods is shown here on this arrow chart. We're irradiating cargo either with photons or neutrons. I'll discuss each of the sources in the upcoming slides. We're going to induce reactions in our material we're searching for. In the case of neutron-induced interrogation, we're looking for, say, fission signatures, which would be photons or neutrons, or neutron capture signatures, which would be photons. When we work with photon interrogation, we'll be inducing reactions like photodisintegration, photofission, and nuclear resonance fluorescence. And after we induce these reactions, of course, we need to detect them. We're largely looking for either photons or neutrons in time domains that are either prompt or delayed. So this is sort of just a general top-down view, if I had to summarize this. So we'll try to cover each of these blocks. And of course, we can take questions along the way or at the predefined breakpoints I have in these slides. So we'll start with neutron interrogation here. Let's start at the beginning. What sources would we use? I know Abbas discussed some of this yesterday. I just wanted to add some pictures in as well. Of course, you can use isotopic sources. You might be familiar with things like americium lithium, plutonium beryllium, and californium-252. Californium being a spontaneous fission source, and then AMLI and PUBI being alpha N sources. And those will give you neutrons. It'll also give you gamma rays. And we can use neutron generators as well, either DD or DT fusion. I have some more details in the next slide. But always with these, you could use either, but consider that isotopic sources are always on, and their strength will vary with time based on the half-life of those sources. And of course, if you have something that requires very high activity, you also need to maintain reasonable security of that source when it's not in use. So again, you might see isotopic neutron sources that are nicely encapsulated. And to contrast, here is a neutron generator with an operator, just to give you a sense of the size that they can make these relatively small now. And since those neutron generators might be, you may not be used to talking about them, I've included an extra slide here. These are basically particle accelerators that leverage fusion reactions. And sure enough, I've included the two reactions here that are most commonly used, DD fusion and DT fusion. Important points to remember here is the neutron energy. So DD will get you a neutron at about 2.4 MeV. DT will get you a 14.1 MeV neutron, much higher energy. Of course, their intensities will vary, and there are usually options to moderate these down to thermal. But of course, adding any moderator will change your flux somewhat because you can have parasitic absorption. These are generally mature technologies and they're commercially available. I already mentioned the small form factor. There are plenty of companies around that have such products. And with these generators, we're going to induce these reactions, and I've decided to plot here some of these common signatures. So first, neutron-wise, we're looking, say, for a multiplicity of fission neutrons. This is not only viable for active interrogation, but also in all sorts of nuclear science. So there's other research that ties into active interrogation and nice lessons learned that these research communities can share. For us, it's really just seen as that clear sign of fissionable material, especially since it's going to be difficult to observe time-correlated neutrons in the passive background, say. And so on the right, I've included a comparison of the energy spectra for prompt and delayed signatures. Of course, you see that delayed signatures are somewhat more complex, but also much lower energy. And of course, prompt signatures are also much more intense. So say, orders of magnitude higher than delayed. So it behooves us to look for those prompt signatures. I don't include gamma ray spectra here, but that's the other signature we can look for. We can either look for captured gamma rays. So say a neutron is captured by a specific isotope and it emits a gamma ray, and that gamma ray will be characteristic of any isotope. So I'll have a slide on that. And we can always look for delayed photons from fission, which are signatures that are also known. The last step, so we induced reactions, we talked about the signatures, and we have to detect them. And it's probably no surprise, we need photon detectors and neutron detectors, and those are often built of different materials to be more effective. Photon detectors, we usually talk about scintillators, inorganic scintillators even. So sodium iodide, which is very common, BGO, or say lanthanum bromide. And I have some pictures here. So lanthanum bromide scintillators, large crystal with a photomultiplier tube attached. Up here are the pins for the voltage divider to attach, voltage divider to get you SHV in or signal out. We can also use semiconductors, which generally have higher energy resolution than scintillators. So HPGE is very common here. You can see all of these different kinds I've included in this picture. Just remember that for HPGE, you not only have the crystal, you have to worry about keeping the temperature low. And so all these containers are those cryostats that have liquid nitrogen. And that's certainly something that would feed into our detection concepts is how easy is it to keep up these detectors, make sure we don't have any operational issues. In the realm of neutron detectors, we can often go with a capture-based detection like helium-3. It's very common. I think I last gave this neutron detection lecture earlier in the summer where we talked about helium-3 reactions. And of course, we can do scatter-based detections, either use plastic scintillators or organic scintillators. So as an example here, you see the still beam crystal here that is stimulated with this UV light. You can see it fluorescing. I think in a lot of these scenarios, probably the most important factors to remember is that we really need high efficiency so that we can maintain that short inspection time. And we can choose these detectors based on our time domain that we're interested in. Perhaps prompt signals, those will be emitted as we interrogate the package or cargo. And so you need to make sure you have acceptable time resolution. If you're looking for delayed signatures, you have the benefit of looking further down the road in the time domain, and maybe you don't need super precise timing, but we'll talk about that in each of these methods. Of course, this slide applies to either photon interrogation or neutron interrogation. So that's some of the basics out of the way. Here is an example of a neutron interrogation concept. It's called differential diaway analysis, or DDAA. This data used an interrogation source that was a DT neutron generator, and they irradiated several targets: uranium, plutonium, and tungsten. And I'll try to talk through each of these panes here, but just remember, in each of these, the black dotted line is the background, and that's if you have your target out but no neutron generator. The red curve marked detector is if you have the neutron generator running but no target out or no source. And then the blue signal lines will be neutron generator irradiating the source. And so let's just talk through each of these curves and discuss what we see. The easiest is probably tungsten. So irradiating tungsten with DT neutrons, you see the initial pulse from the neutron generator. You see how high the signal is. And then, of course, the signal dies away just based on the electronics. And then you return back to background. So once the neutron pulse is done, there's no remaining radioactivity because there's no fission of tungsten. There's no neutrons, thermal neutrons floating around to activate the tungsten, because that reaction would not be common. And so as a result, your neutron counts just return to your background where it was before you even turned on the neutron generator. We'll move to something slightly more interesting material: depleted uranium. Depleted uranium can undergo neutron-induced fission, especially from fast neutrons. And so you can see we have the neutron pulse, and you can see in the blue curve how it takes much longer to return to that background. So these are, say, fission chains that are continuing on after the pulse of the neutron generator. Take the next step further. If we enrich the uranium, now there's more uranium-235, and that is capable of thermal neutron-induced fission. So here, after the initial neutron pulse occurs, we have a much longer die-away here, and that's because those fission chains can continue on and create more neutrons. It's because neutrons that are thermalized in the room or the testing area can get back to the uranium and cause more fissions. And that's what causes this tail to look so different from these non-fissionable, non-fissile materials, I suppose you would say. The final case, of course, will be this plutonium case. You'll see much the same with the tail, but also you can see how much higher the background is compared to the detector curve. And that's because plutonium has a spontaneous fission neutron rate. So here, just from this data, you could already see, you could perhaps tell there's some neutron emitter because the dotted black line, the background, is just so much higher than your typical experiments. So that's a lot of information. Be sure to post questions in the chat and we can address them if anything's unclear. There's a few breakpoints here where I'll be able to talk, but that sort of compares what data you might see from these differential die-away experiments. The second neutron concept I added here was the prompt gamma activation analysis, or PGAA. So this is a neutron interrogation with a photon detection method. So here's an example system on the right from this publication, where you would send packages through a DD neutron generator, and then you use an HPGE to detect the photon emissions. It's especially valuable for seeing hydrogen-rich or neutron-rich material. What's happening is these neutrons are captured, so like N-gamma reactions. There's also, say, NP and N-alpha reactions that are possible, but those reactions are emitting those characteristic gamma rays. And so you could look at your gamma ray spectrum, like I'm shown here, to identify presence of hydrogen, carbon, nitrogen, and oxygen. Those are very common isotopes for contraband. And to demonstrate, there's this spectrum on the lower left here. It's channel number, so it's not energy calibrated here, but you can see in the comparing the, let's see, Teflon blank and these dotted lines, you can see all these gamma rays that are emitted at about 2.2 MeV, because that's the characteristic gamma ray from hydrogen neutron capture. And you can see this dotted series is well above system background, either here in the flat area or just one of these peaks added here. Another metric that this publication at least shows is a nitrogen mass fraction curve. So you're measuring the nitrogen signatures here. And you can see as you increase the neutron mass, or excuse me, the nitrogen mass fraction, your count rates are increasing. And so they've measured 3 different energy lines, all, let's see, 5 MeV for 2 of them and a 1.8 MeV for these triangles. And they have their linear fits here. And so you can use this to intuit what these packages contain. This is the last neutron. Let me double check neutron slide. Yeah, so I see a few questions here. We can go through that quick. Let's see, does the enriched uranium die out solely because of the higher cross-section of U-235 at thermal energies? Let's go back to the slide. Yes, so that's related to the persistence of these fission chains here, and that'll be influenced either by the neutrons that are just produced in the sample, and U-235 has these higher fission cross sections, but also fission by thermalized neutrons in and around the experiment. So yes, you're right. I see a second question. What determines whether I should use thermal or fast neutrons in my interrogation? Probably most likely related to the reactions you're looking to leverage. It's discussed often about something like fissile materials. Of course, that means like thermal neutrons would be quite useful. Some of these, say, contraband searches would be require fast neutrons just based on the thresholds of these reactions. So it's going to be entirely up to what you are looking for, what material or contraband you're looking for. So hope that answered the questions there. Oh, would you mind explaining why plutonium has higher background counts again? Okay, so back on this slide, here's the plutonium. So again, background BKD is when you have just your target or your radiation source. So, you know, you're in this case, the reactor-grade plutonium and depleted uranium, and you're not operating the neutron generator. And so if you're just measuring a plutonium source with a neutron counter, you're going to detect neutrons from spontaneous fission reactions. And so that's why that background is much higher. Compare that to uranium, where spontaneous fission is not common for that isotope. And so that's why your background is much higher. So I'll give a few more seconds if anyone has any more chat questions. Otherwise, I can move on to the photon active interrogation section. All right, sounds like a good time to move on. Now we'll talk about some photon interrogation methods and concepts. Again, we'll start at the beginning. What sources would we even use for these reactions? There are plenty of isotopic sources that are commonplace. If you work with detectors, you're probably familiar with things like cesium-137 and cobalt-60. Cobalt-60 is also used for, say, sterilization efforts, but they're not generally used for photon active interrogation applications, either because they'll be emitting a lot of radiation in all directions as opposed to some like directionally desired, so like a beam. The energies are often insufficient for some of these nuclear interactions. So if you look at the giant dipole resonances for photodisintegration or photofission, you'll find that you need to have energies greater than 5 MeV, and consequently, it's difficult to find an isotope that would match that energy. And just like with the neutron sources, source security is always something we need to have in our minds. The Curie sources need to have appropriate security. And so it's much more prevalent in photon active interrogation that we see X-ray generators or gamma ray generators. And so these sources are typically like Bremsstrahlung sources. So they're using the Bremsstrahlung reaction. There is also tunable monoenergetic photon sources, which are more on the research stage now. And so 2 examples of commercially available systems would be like an IBA Rototron shown here. You maybe see from the ladder, see the scale of that system. There's also like Varex linear accelerator. This doesn't establish good scale, but it's probably about certainly not, maybe similar size to a neutron generator, larger certainly. And so again, these generators or these accelerators are probably less well known than isotopic sources. So here's an extra slide. These linear accelerators have electrons that are produced from a cathode source. They're accelerated by electromagnetic waves to high kinetic energy. And those are then going to strike a high electron density target and undergo radiative losses and produce Bremsstrahlung radiation. These are sort of broadband long energy distributions with long tails. So you see here, here's a logarithmic plot of a 5.3 MeV Bremsstrahlung beam. So 5.3 MeV electrons into a target and undergoes radiative losses. Important thing to notice is that the 5.3 MeV photons are actually quite small. It's much more likely that you get these lower energies. And this brings about 2 points. One, this is a continuous energy spectrum, quite different from neutron generators, which will provide nearly monoenergetic energy distributions. And two, perhaps many of these photons that are produced by your Bremsstrahlung sources are below photonuclear thresholds. So thinking back to those photonuclear cross sections that Abbas showed yesterday. And so that means having a reasonably intense source to get enough flux above your desired energy, but it also means you'll have a lot of low energies, photons that are just contributing to dose. So always think about that within each of these applications. So establish our source. Now we'll talk about some concepts here for photons. I include a slide here for nuclear resonance fluorescence. That is photon interrogation, where we expect to see some photon detection. Here we use these high energy photons to excite resonances of the nuclei. These are unique and discrete energies. You can think of them sort of analogous to characteristic X-rays. So as opposed to electrons reaching discrete energy levels and then emitting X-rays that are of characteristic energies, this is instead a nucleus achieving a excited state at a discrete level and then relaxing back down to its ground state, emitting a photon of specific energy. And so a layout might look like an X-ray source of suitable energy and flux that's collimated to irradiate an object. That object will produce those photons and you have to detect them and an appropriately shielded detector. Example data shown here. So here they have compared two NRF spectra. The black here, which is hard to see, is just a manganese sample, but you can see already they're detecting, this looks to be somewhere about 1760 keV peak, and then another one that's much closer to 1900. And then they add in an HEU plus manganese and PET sample. And now you see many more peaks, and you see an added continuum probably caused by all these different interactions from all these peaks. And so all these green arrows point out to these characteristic gamma ray lines that are emitted from these NRF reactions. And so you could pick out these peaks and link them up to isotopes and identify this. So some of the literature talks about these systems have potential to detect quite small quantities and even in shielded systems. But of course, there's always some challenge or disadvantage. In this case, a photon background would be very prohibitive due to the likelihood of these emissions. And so for a Bremsstrahlung source that emits a wide energy range of photons, maybe you find that it's hard to pick out these peaks. Another example I included is prompt photofission neutron detection. So think of that as a photon interrogation and neutron detection. Here I have some data that involves a linear accelerator Bremsstrahlung source that is interrogating a depleted uranium sample. Upper right, this is a pulse rate discrimination plot from a measurement, just to drive the point home that when you're looking for prompt signals, you have to deal with pulse pilot. And so the way this plot works is based on the different scintillation physics for, say, still beam. You can put a discrete or you use a discrimination line and say if a pulse shows up in this region, I can classify it as a photon. If it's above in this region, it should be neutrons. Usually we see two nice peaks. You can at least see a nice photon peak here, but because of pileup, we see everything's just washed out in this region, and it's hard to pick out which of these are neutrons and which of these are pileup regions or pileup events. So we had shown that there's intense pileup, and we also have some work that improves this detection capability using machine learning algorithms. So if we use some machine learning to look at the waveforms that create or contribute to these data points on this 2D histogram, we can actually recover data from them and reclassify them. So, so a machine learning algorithm classified all these pulses as photons. So pick that out from this plot. And for neutrons, it was actually pull out a sort of subtle neutron band here. We'd usually expect a band in this region where my laser point is going. So it's an interesting work. And of course, there's plenty of research in this area. So I'll go through a summary, and then of course we can take more questions, but here just a top level overview of all these methods. We're irradiating cargo with either photons or neutrons. We have to induce reactions, things like fission, capture, photodisintegration, nuclear resonance fluorescence, and then we have to detect these signatures. And that means using, again, looking for photons and neutrons. And we can leverage different time domains to pick out signals that work well. So prompt signals, which will have to deal with pileup, but there's potentially much more signal there. Or we can look in the delayed time window where you don't have to compete with the radiation interrogation source, but the overall source terms are quite low. But overall, this has potential to improve the capability to detect fissile material and contraband, especially in the scenarios we've outlined. And just always to remember, there's always challenges to address, things like dose to operators of the public, cost of these systems, and of course, active areas of research all seek to alleviate these issues. So that's the end of my slideshow. Thanks for listening. Go ahead and post some more questions in the chat. We can talk for a bit. Let's see, is the slow die out of U235 due to delayed neutrons? That's probably back on this slide. Yes, that ought to be a factor, but I think perhaps more prominently is just the fission chains that persist. Let's see, which method is more efficient in inspections, prompt gamma neutron activation analysis or nuclear resonance fluorescence using X-ray source? So it's hard to compare these methods. I think it's important to say the prompt gamma neutron activation analysis, like you have to use a neutron source for that. NRF has to be an X-ray source. And I think you'll just be restricted to what materials you're looking for. So I don't know off the top of my head the NRF resonances for all isotopes. You'd have to look up what if you have the right energy of photons to excite those resonances. So sorry, that's a bit of an open-ended question. So I guess I'd just say, like, just consider which material you're most interested in, and then pick out a method for that one. Let's see, it seems like different techniques are more sensitive to certain materials. Do we have to combine more than one technique in monitoring cargo containing different kinds of goods? That's a good point. Yeah, I think, yeah, there just has to be some optimization and you have to decide on it for your systems, especially if you're considering like dose. If dose is a great concern, perhaps running six is an exaggeration, but running a photon source and a neutron source simultaneously to interrogate maybe that creates too high of a dose rate to the public. So that's part of the engineering process, deciding perhaps which of these modalities match well or complement each other. You may have to combine techniques. I think maybe perhaps another point is, I don't know this to great detail, but using neutron interrogation, I suppose you have some opportunity to activate other materials or perhaps cause material damage to like electronics. So perhaps even the type of cargo you're looking to inspect may steer some of your decision making. It all depends on dose, I think, in that case. And yeah, feel free to send me an email if you have a question comes up. Email's on the bottom of the slide, and I'm sure you can find it through the summer school as well. So thanks again for listening and asking your questions. I can stay on for a few more minutes, but otherwise we'll probably maybe about like 1:40 we'll call it.